All right. Well, thanks everyone for coming to another TCS Plus talk. Today we have the huge pleasure of having Roei. He's a postdoc at the IAS and DIMAX. Has really done a lot of fantastic work on complexity theory and circuits, derandomization. And today he'll tell us about his paper on hardness versus randomness revised. I'll let Roei introduce, but before we begin, let me just say that feel free to ask any questions. I'll be monitoring the chat if you want, or just feel free to unmute yourself and go ahead and ask. And finally, let me thank the rest of this organizers at TCS Plus. This includes Clement Canon, Rachel Cummings, Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Tomas Vidik, Noah Stevens Davidowitz, and David Weiss. It's quite a long list of organizers, but okay. With that said, please, Roei, take it away.
Thank you very much, Eric. Thanks for the introduction, and thank you for the opportunity to speak here. Hello, thanks to everyone tuning in, and hi to everyone watching the recording too. My name is Roei. This talk is titled Hardness versus Randomness Revised, Uniform, Non-Blackbox, and Instance-Wise. It's based on a joint work with Lijie Chen from MIT, whose picture you can see here in the bottom. And I invite the people here attending to please feel very comfortable to stop me at any point for questions. It is really not crucial for me to cover all the technical contents in this talk. So if we want to pause on the high-level parts, the messages or the statements, please feel comfortable. And the main thing that we're going to say in this talk is a new version of the main paradigm in the randomization. We're going to revamp the main paradigm such that it will work in a non-black box fashion. And it will result in a general framework for doing hardness versus randomness in a non-black box fashion. For example, the general framework will have instantiations that connect the BPP equals P conjecture to a new type of lower bounds for uniform algorithms. Another instantiation that we will see is what we call a free lunch derandomization. Derandomization that incurs effectively no time overhead at all. And other instantiations that we won't focus on include slower derandomization versus weaker lower bounds, average case derandomization, derandomization of weak circuit classes, and so on and so forth. But really the second point here is that will be a general framework. And I'm going to start with background, and in particular with two main motivating questions for the talk and for the results. So let's recall the hardness versus randomness paradigm, which is in every complexity one-on-one course and textbook. This is the main paradigm in derandomization. And it was introduced in the early 80s and crystallized into the current form that we know today and that appears in textbooks throughout the 90s. And later on, in the late 90s and 2000s, a sequence of very impressive and interesting papers worked it out to get the right parameters, to extend it, to finalize it into the form that we are familiar with. And the main focus of this framework is to show an equivalence between explicit PRGs for circuits and explicit lower bounds for circuits. And the PRGs are then used for derandomization, for example, for showing that BPP equals P. So we can see from this line of works that lower bounds for circuits are equivalent to PRGs for circuits. For example, the famous result of Impagliazzo and Wigderson shows that if exponential time does not have circuits of small exponential size, then there is a polytime computable PRG with logarithmic seed for circuits. And this is an if and only if. And as a consequence of such PRGs or lower bounds, BPP equals P. And throughout the talk, whenever I say BPP equals P, I mean the promise problem versions. It's promiseBPP equals promiseP. I'm just going to use shorthand. And a secondary focus of this line of works is an equivalence between two weaker objects, specifically between lower bounds for uniform algorithms rather than circuits, and PRGs for uniform distinguishers rather than PRGs for circuits. So both the lower bounds and the PRGs here work against adversaries who are uniform probabilistic algorithms rather than against adversaries who are non-uniform circuits. And this type of PRG can be used for average case derandomization. For example, for showing that BPP equals P on average. You can simulate BPP deterministically while being correct on 99% of the inputs. So another result from the 90s, and again, from Pagliazzo and Wigderson, and for simplicity, I'm waving my hands and ignoring some technical issues, is an equivalence between the lower bound, exponential time is hard for BPP, and the existence of a PRG for uniform distinguishers that has C then to the epsilon, which is equivalent to showing that BPP can be simulated on average in sub-exponential time. Let me zoom back for a second. So this is the landscape of what we know. The top row here is the equivalence between lower bounds for circuits and PRGs for circuits. It implies that BPP equals P. And below it, the bottom row is an equivalence between lower bounds for algorithms and PRGs for algorithms, which is equivalent to average case randomization of BPP. And you can notice that there is a glaring gap here. There is a crucial missing piece because the thing that we care about the most is the randomization, BPP equals P. And this is kind of, it looks like a side deal in this entire map. This map gives sufficient and necessary hypothesis for two other objects, but it does not directly address the question of which hypotheses are sufficient and necessary to de-randomize BPP. And this dates back to a classical open problem. The classical open problem is whether or not PRGs, as in the top row, are necessary for the randomization. So to explain this problem, PRGs yield black box derandomization. What do I mean by that? Well, the PRG does not really need to see the input or the machine in advance. We first prepare the pseudo-random set, and then later on, we evaluate the machine on this set of pseudo-random strings. So the set of pseudo-random strings does not depend on the machine or the input. And the question is whether or not this is an overkill, because it looks intuitively like it might be an overkill. And for non-deterministic derandomization, for example, for showing that MA equals MP, we essentially know the answer. So PRGs are essentially necessary. And this is a key step in the proof of the algorithmic method pioneered by Ryan Williams in the last decade, and it follows the result, earlier results of Pagliazzo, Cabanets, and Wigderson from about 20 years ago. But the point is that for standard derandomization of BPP, for example, showing that BPP equals P, we really don't know. We don't have any unconditional results either way. So we are left with the question of, okay, which are sufficient and necessary hypotheses for derandomization, regardless of PRGs? And jumping ahead, our first main result will address precisely this lacuna. It will connect the statement BPP equals P with a new type of uniform lower bounds that we introduce. And needless to say, this will be non-blackbox derandomization that does not use the classical PRG approach. Let's move on to the second motivating question. And this is a great recent question. So BPP equals P means that for any time-bound T, we can de-randomize probabilistic time T in deterministic time T to the constant, C. But really the statement does not yield any guarantees about the constant. For example, we could yield probabilistic time T we could de-randomize probabilistic time T in deterministic time T to the million. The polynomial overhead may be huge, vastly impractical. And Doron, Moshkovitz, O, and Zuckerman recently introduced the question of, can we de-randomize faster? Can we have some guarantees on the actual cost of the randomization? What is the overhead that we need to de-randomize? And of course, the obvious question that comes to mind when you see it is whether it's possible to get a free lunch. Can we de-randomize without paying for it at all? And Doron et al. Showed that under very strong circuit lower bounds, we can de-randomize with essentially a quadratic overhead. Probabilistic time t can be de-randomized in deterministic time roughly t squared. And the follow-up work, again, Fligia and mine, show that under one-way functions and under lower bounds that are necessary if you use PRGs, so these are reasonable lower bounds, probabilistic time t can be de-randomized in deterministic time, essentially n times t, where n is the input length. So for a large t, this is great because the overhead looks really small. But for a small t, this is a problem. For example, if we want to de-randomize linear time, we just get back to quadratic overheads here. And of course, the question is whether or not we can de-randomize probabilistic time t and deterministic time t. And following up on the previous work, we've got three answers here. First, assuming reasonable complexity theoretic conjecture, no. This overhead of n is necessary. And the conjecture that I'm talking about is sharp n-SETH, which is, it belongs to the family of exponential time hypotheses. Okay, so we can de-randomize on the worst case with such overhead. However, we can de-randomize under some assumptions on average without overhead. So we can remove the overhead if we are willing to settle for making a few errors, being correct on 99% of the inputs. And another observation is that being correct on average in the sense of being correct over all polynomial time distributions, polynomial time sample distributions, cannot be done in the black box approach. It inherently requires using a non-black box approach. And this is where the current paper comes in. So under appealing uniform lower bounds that we will see next, randomness is what we call informally indistinguishable from useless for decision problems and for natural search problems, which in a bit more detail, we can de-randomize probabilistic time n to the k effectively in deterministic time n to the k plus epsilon, for epsilon that is as small as you want. And what does effectively mean here? Well, it means that, okay, we simulated any problem in probabilistic time n to the k in deterministic time n to the k plus epsilon, and no polynomial time algorithm can find a mistake with non-negligible probability. So every polynomial time algorithm that tries to find an input on which the derandomization errors does not succeed except with negligible probability. And the second part of the result will be that for any dense property, we can explicitly construct objects that have this property in time that is almost identical to the time that it takes to check the property. We will go over this in a bit more detail later. This will be essentially our second main result that we want to talk about. And what is our main contribution? What is really going on here is that we introduce a new way to do hardness versus randomness. And this new way yields both of the results that I just talked about and a bunch of other results too. And indeed, this new way is what we call with these three adjectives, uniform, non-black box, and instance-wise, that I'll explain. All right, so let me explain the high-level technical approach behind this new way to do hardness versus randomness. So let's first recall the textbook approach. We want to simulate a probabilistic machine M on a given input. And without loss of generality, we can assume that the input is a description of a circuit, and that M is a machine that draws a random input to the circuit and evaluates it. And this is just a complicated way to use a complete problem. So what I'm saying is that the setting that we have in mind is that we are given as input a description of a circuit C, and we want to approximate its acceptance probability up to an additive error of, say, 1/10. Let's draw this. Here is on the left our input, C, a description of the circuit C. And the distinguisher, the adversary that we have in mind is this circuit C on the right, with either a random input or a pseudo-random input. And how does the textbook approach work? Well, first, we sit down and write the truth table of a function that is hard for all small circuits. We just sit at home, take a pen and paper, and write down the truth table of this hard function. Then, we apply a standard hardness-versus-randomness transformation that you know. Nissan-Wigderson combinatorial designs, error-correcting codes, all the standard textbook tools, which transform this string, this truth table of a hard function, into a pseudo-random set that I denoted here by R1 up to Rn. And what do we do next? Well, we plug in these pseudo-random sets as inputs to C. And we hope that C behaves the same on R1 up to Rn as it behaves on a truly random input. Any questions about this? Good, so I'm going to be even a bit more specific because I really want to hammer in this point. Here is the derandomization algorithm that we get from classical results. Given C, we compute a hard truth table. We can do it since we have the assumption that there is an explicitly computable hard function. We transform it to a set of strings, R1 up to Rn, using error-correcting codes and combinatorial designs or whatever favorite hardness-versus-randomness transformation that you have in mind. We evaluate the input circuit C on this pseudo-random set, and we output the majority vote. And correctness is via standard reconstruction arguments, saying that if the circuit C is a distinguisher for this pseudo-random set, then we can compute F by a small circuit that depends on C, which is a contradiction because F is hard. Okay, we went over this in detail, and now I want to look at it again. And I want to claim that there is something really annoying going on here. You look at this algorithm. The algorithm first gets C, then forgets all about it. Writes down the truth table F, transforms it into a pseudo-random set, and then in the end, it remembers that originally it had the circuit C. It pulls it back from the shelf, and it evaluates it on the pseudo-random set. And this is the black box property that I mentioned before. The pseudo-random set does not depend on the circuit C, because we just produced it from thin air. We wrote down the hard string F by ourselves, not relying on anything. And the main innovation in this work is one crucial change in this paradigm. We get the input C, and instead of writing down F from thin air, F is now a function of C. So we will apply a function to C to get a hard string. And from there on, we will continue to use this hard string as a basis for producing a pseudo-random set. And the key point, to repeat it, we are going to use information from the input C in order to produce the pseudo-random set. And of course, we adjust our expectations accordingly. Since the pseudo-random set depends on C, we expect it to only be good for C. So the pseudo-random set that we produce from C will be good for the specific circuit C. Let's see. Let's just get back here. Note that this is more than enough for the randomization. Because we have the circuit C in our hand, we use it to get a pseudo-random set, and then we evaluate the same circuit C on this pseudo-random set. And as pointed out by an insightful reviewer, it's not that this is some kind of dramatic idea that has never been thought of before. This is an obvious thing that you would try. And it has been tried for at least 20 years, dating back to a work of Goldreich and Wigderson in 2002. But the point is that it was not known how to take advantage of the input. The line of works following Goldreich and Wigderson, which is called typically correct derandomization, either had to use circuit lower bounds as hypothesis or deduced conclusions that are stronger than what we are about to see. What we will see today uses new ideas and new technical tools to materialize this idea and make it work in the general settings that we care about and for sufficiently strong and interesting conclusions. And it's not to add to what I just said, it's not only that people have been trying to materialize the idea, it's that there is even an abstraction ready-made that abstracts this idea. It was introduced by Goldwag, and it is called targeted PRG. You can also think of a targeted HSG, heating set generator. And this is a PRG that gets as input a circuit C and efficiently computes a set that is pseudo-random for C. And Goldwag showed that this is the existence of a targeted PRG is both necessary and sufficient for the randomization. And indeed, this is precisely what we do in this work. We materialize this abstraction. And to materialize it, we are going to need some creative ideas. It's not that simple. So f of c, I did not promise anything about it. I did not tell you what f of c is. So for example, f of c could be, you can think of a hard function, and then what we will use as the information for producing a pseudorandom set is going to be the tableau of a machine that computes the hard function. Or, and this is really waving my hands, the prover strategy is in a proof system that asserts the value of the hard function. So we are going to use some kind of information here as the basis for producing the pseudorandom set for C. And indeed, there are two non-black box elements in this approach, because using the term non-black box is overloaded. First, as I just said over and over again, we are going to use the information in the input C to produce pseudorandomness for C specifically. And the second notion of non-black boxness here is that instead of just applying the hard function as a black box and using its evaluations, we are going to use essentially the tableau of the computation of the hard function. So we are going to use non-black box properties of the computation of the hard function on C as a basis for producing a pseudorandom set. Let me now go back to this and ask if there are any questions about this point, because this is the main point in the talk. Great, thank you. Let me move on. So I'm going to state the two main results that we get with this approach and that I'm going to focus on the current talk. So the general form of our assumptions is going to be roughly the following. Okay, recall that we are not working now with the classical approach of circuit lower bounds. We are using new hardness assumptions. So we are going to assume that there exists a multi-output function f mapping, say, n bits to r of n bits, where r of n is, I don't know, n log n to the epsilon, definitely a super constant number, such that the function is computable in some deterministic time, but is hard for smaller probabilistic time. For example, it's computable in deterministic time poly t, but hard for probabilistic time t. And since there are a lot of assumptions in our heads when thinking of hardness versus randomness, let me hammer in the point that this is a very straightforward and natural assumption. It just says that there exists a function f that you can compute in deterministic polytime, but given x, it's hard to print the string f of x quickly. So we are just concerned with the complexity of taking x and printing the string f of x. And the precise meaning of hard will differ across our results, and sometimes we'll put more constraints on the complexity of f, but this is the main form, a separation between deterministic uniform algorithms and probabilistic uniform algorithms running in shorter time. But this separation happens for multi-output functions. And let's see the first and main instantiation of this. So I'm going to define a function that is hard on almost all inputs. So a function f, which is for simplicity length preserving, is hard for a class A of algorithms, uniform algorithms, on almost all inputs, if every algorithm from the class fails to compute f on 100% of the inputs that are sufficiently long. So recall, usually when we talk about hardness, we mean that every algorithm fails on some input. When we talk about stronger notions of hardness, we say, oh, okay, every algorithm fails on 49% of inputs. maybe even of 99% or 99% of inputs. Here we require that every algorithm, starting from a sufficiently large input length and onwards, fails to compute F on 100% of the inputs. In other words, every algorithm succeeds only on finitely many inputs, say the first 1,000. So each and every input fails the algorithm. And this looks like a crazy strong notion when you say it for the first time. And it's not even clear that it's realizable. So as a first observation, it's realizable, it's even easy, it's something that you can get with diagonalization. So there exists a function that you can compute in time n to the k plus 2, say that is hard for time n to the k on almost all inputs. This is not difficult to show. The point is that we have multiple outputs. So we are going to use every output bit to diagonalize against the corresponding machine. And each machine will get diagonalized again starting from some sufficiently large input. So this notion that looks crazy at first sight is actually a natural notion that you can get. And more to the point, the observation motivating the first result is that if promiseBPP equals promiseP, then for every constant C, there is a multi-output function computable in deterministic polytime that is hard for probabilistic time n to the C on almost all inputs. I see that there is a question in the chat.
Yeah, I can read out the question.
Yeah.
The question asks, if it is 100%, why do you say almost all inputs?
Oh, so for every machine, I can always hardwire the first 1,000 inputs. And then the machine is successful on the first 1,000 inputs. But this notion of hardness says that except for these finitely many, because finitely many you can always succeed, the machine fails on all other inputs. So almost all here means all but finitely many. Was that clear?
Yeah, I think so. Yeah.
Good, thank you very much. Okay, so I'm now saying that if PPP equals P, then almost all inputs hardness against probabilistic time, say n to the 100, is necessary, it happens. So almost all input hardness is necessary for showing that PPP equals P. And really the main result is that it also suffices for showing this statement. So the existence of such F that is computable in deterministic time, but hard on almost all inputs for smaller probabilistic time, suffices for promiseBPP equals promiseP under one additional constraint that I'm going to now explain. So this is the formal statement of the theorem. So if there exists an F that is hard for probabilistic time n to the 100 on almost all inputs, and is computable by uniform circuits of polynomial size and fixed polynomial depth, say n squared, then promiseBPP equals promiseP. And I'm going to say in advance, the notion of uniformity here is log space uniform circuits, but these are not, this problem is not in log space. It's just a relaxed notion of uniformity. So if you are not familiar with it, ignore it. Just read the statement as talking about uniform circuits of polynomial size and fixed polynomial depth. So the additional constraint here is that the function is computable not only in deterministic polynomial time, but in deterministic polynomial time and mildly in parallel. So n squared steps. And combining these two results, we get the middle row that we saw in the diagram before. We get a connection between derandomization, promiseBPP equals promiseP, and lower bounds for probabilistic algorithms on almost all inputs. This is the connection that we hinted before. And the only gap that remains right now from a full equivalence between these two notions is that one direction requires the hard function to be computable by circuits of depth, say, n squared. And let me do a short detour and get back to this precise point. The short detour is just playing with this result a bit. It requires work, but in our minds, as seeing the results now, we want to see that we can play with the result. It extends, it generalizes, it scales, it's robust. So a meta theorem is that this result is robust and it scales nicely. And moreover, when we play with this result, scaling it, moving it to other settings, so on and so forth, the gap between the necessary hypothesis and the sufficient one significantly narrows. In some settings, it is very close to a full equivalence. So for example, let's look at this result, saying that if there is a function computable in exponential time that is hard on almost all inputs for essentially BPP, probabilistic polynomial time, then we have a slightly non-trivial derandomization of RP. So RP can be simulated infinitely often in time, say 2 to the n to the 100 for this fixed 100. This is a slightly non-trivial derandomization. And at first glance, you look at this and you say, okay, we just scaled up the hypothesis and the conclusion. Now we're talking about weaker lower bounds and slower derandomization. But if you look carefully, what's going on here is that we are not assuming anything about the depth anymore. We remove the constraint. So this is almost a full equivalence here. Basically, the only gap from a full equivalence is that here we only know how to derandomize RP rather than BPP. And another extension, which I won't go over in depth, is that basically this entire hardness versus randomness with almost all input lower bounds scales to weak circuits for NC circuits. So if we assume almost all hardness for probabilistic uniform NC, we can de-randomize probabilistic uniform NC in uniform NC. So just like the original hardness versus randomness framework that was black box scales to weak circuit classes or to slower time, this result scales too. And in addition, the result is robust to perturbing the hypothesis a little. Because you can ask, okay, what happens if F is hard, not on all inputs, but on all but really a tiny few, on all but 5, on all but 1%, on all but an exponentially small fraction. Basically, wherever you get hardness, this is where you get the randomization. If the function is hard with respect to a distribution X and with hardness 1 minus mu, we de-randomize BPP on average over the distribution X with success precisely 1 minus mu. The hardness and the success translate perfectly. So rounding back, I return to the previous point. This connection between worst case derandomization, almost all inputs lower bounds is general, it is robust, and it seems to be the right class separation for derandomization intuitively. It is a special case of broad and not very precisely defined conjecture by Cozen in the 70s, which says that for a pair of circuit classes, showing that one circuit class can simulate the other circuit class, for example, derandomization, is equivalent to showing lower bounds in that class for the bottom class. For example, here, showing almost all inputs lower bounds for hard functions computable in deterministic time against smaller probabilistic time. It's a natural connection to expect that deterministic machines can simulate probabilistic machines if and only if they can compute a hard function for probabilistic machines. Really, the only new point here with respect to this conjecture from the 70s is that the hardness is on almost all inputs. The function has multiple output bits. And one curious thing to note is that I keep repeating this almost all inputs lower bounds, and it's indeed very odd to have an unstudied type of lower bounds in theoretical computer science in 2022. This isn't something that we'd expect, but we found no previous mention of this type of lower bounds. All right, let me now move on to the second main result, which is the second instantiation of the new hardness versus randomness and a black box approach that I'm going to talk about today. So for a function f, we define its k-wise direct product as the function that takes k disjoint inputs, x1 up to xk, and evaluates the original function f on each of them independently. So the ky-wise direct product outputs k bit, which is just f of x1, f of x2, yada yada, up to f of xk. And the meta claim, and one of the main reasons we're interested in these functions, is that the ky-wise direct product is much harder than the original function. Because intuitively, we need to compute the original function on k independent instances. I'm going to talk about one notion which it is much harder. So let me introduce a definition. A probabilistic machine M approximately prints a function f on input x if the probability over random coins and over an index that mx of I equals ff of x of I is over 99%. Or in other words, intuitively, with high probability, the machine prints a string that agrees with f on almost all bits. And what we want to think about here is the notion of failing to do that. So we say that a machine fails to print f of x if the machine prints a string that has at least 1% corrupted entries. This is the notion of failing to approximately print. And the following is an unconditional result. It's in a simplified version. I'm hiding some details, but it is a direct product result saying that if f is hard, then the ky-wise direct product is hard to approximately print on the vast majority of inputs. So take f to be a mildly hard function on average for probabilistic time t, meaning that every probabilistic algorithm running in time t fails to compute f on 1% of the inputs. Then take k to be a large constant and consider the ky-wise direct product. And we say that every probabilistic algorithm running in time approximately t fails to approximately print the ky-wise direct product on the vast majority of the k tuples that it is given as inputs. So this is the flavor of a direct product result that I wanted to talk about. This is unconditionally true for every function that is hard for probabilistic time t. You take the ky-wise direct product, and now it is hard to approximately print. On 99% of the input, it's hard. Questions about this? Okay, so a conjecture that is popular and is studied, it is called the strong direct product conjecture, is that the ky-wise direct product is hard also for larger time, rather than only on a large percent of the inputs. For example, imagine a function whose complexity is exactly t. Now take the ky-wise direct product. You can imagine that to compute the ky-wise direct product, maybe for some functions, you cannot do better than spending time t on each and every input. So the time complexity of the ky-wise direct product will increase to k times t. This cannot hold for every function, but it is conjectured to hold for some functions. And the assumption that I will now introduce for the second main result is a very weak form of what I just said. So we say that the function f has the mildly strong approximate direct product property for time t if, when taking the ky-wise direct product, its time complexity slightly increases. To be more precise, for every k of the form n to the epsilon, there is some increased delta, such that every probabilistic algorithm running in time slightly larger than t, t to the 1 plus delta, and the rest of the sentence is what we saw before, that is unconditionally true for any function. Every such algorithm fails to approximately print the ky-wise direct product of 99% of the k tuples. So this hypothesis says that for some function f, we can strengthen the unconditional result by saying that it holds even for a slightly larger time bound, t to the 1 plus delta instead of t. Note that we do not require the time bound to be maximal, t times k. We're just saying that some slight increase in the time complexity happened. And now we can state the second main result. We call it free lunch derandomization. So assume that one-way functions exist, standard one-way functions, the basic version against polynomial time algorithms. And also assume that there exists a function. Let's see, okay. There exists a function that is computable in time t to the 1 plus epsilon, but has this direct product property, the mildly strong version, for time t. So intuitively, it's a function that you can compute in time t to the 1 plus epsilon deterministically, that is hard for probabilistic time t, and that if you take its k-wise direct product, its time complexity increases a bit with respect to approximately printing on average. Then, and now we reach the conclusion, probabilistic time t can be simulated on average in deterministic time t to the 1 plus something that grows with epsilon or with epsilon. And what does this average mean? It means that on average over the uniform distributions, there are very few mistakes, say 1% mistakes. And this is a free lunch randomization in the sense that we do not pay in the time complexity. We de-randomize probabilistic algorithms running in time t in deterministic time t to the 1 plus epsilon, and we incurred 1% mistakes. And something that is interesting about the statement that is written here is that the hypotheses look quite mild and appealing. One-way functions is just one-way functions, standard as you get. The existence of a function that is like this, computable in time t to 1 plus epsilon, but hard for probabilistic time t, is necessary for such randomization. We are just adding the hypothesis of this mildly strong direct product, and poof, we get the randomization with basically no time overhead at all, the small fraction of mistakes. And using the same flavor of assumption, just a stronger version that I'm not going to describe in detail, we can get a stronger version of the conclusion. So under the same flavor of hypothesis, one-way function and these functions, one-way functions and the function with a structure similar to the k-wise direct product that I just mentioned, probabilistic time t can be de-randomized in deterministic time t to the 1 plus epsilon in the following sense. It's on average with respect to all polytime sampleable distributions. No polynomial time algorithm can find with non-negligible probability an input on which this free lunch randomization errors. And this is what I referred to earlier as randomness is indistinguishable from useless in this context. We can simulate randomness without paying for it at all, and no efficient algorithm can find an input on which we erred, except with negligible probability. And a second part of this second result refers to explicit constructions. So under the same assumption, the cost of explicitly constructing good objects is not more expensive than verifying that an object is good. So let's state this formally. So take a property pi of good objects and assume two things about it. Assume that you can recognize a good object when you see it. So pi is decidable in probabilistic time n to the k. You give me a graph, I tell you if this graph has this nice property. And also assume that the property is somewhat dense. For example, just for simplicity, say that over half of the strings have the property. So most graphs have this nice property. In this case, we can efficiently and deterministically print objects with this property. There exists a deterministic algorithm that gets input 1 to the n and prints a graph with this property, and its time complexity almost matches the time that it takes to just verify that the object has the property, that the graph is good. Any questions up to this point? Okay. So what did we do so far? I gave some context, I gave motivating questions. I described the high-level approach of producing pseudorandomness from the input, and I stated a couple of results. Now in the technical part, I want to give a sketch, high-level sketch of the proof of one result that I mentioned. the proof that connects derandomization to almost all inputs hardness. So let's remind ourselves of this result. So if there is a function that's hard for probabilistic time n to the 100 on almost all inputs, and is computable by uniform circuits of polynomial size and depth n squared, then promiseBPP equals promiseP. And let's prove it. So to show our conclusion, it suffices to show that promiseRP equals promiseP. These are classical results. And to be more specific, it suffices to solve the following problem in deterministic polynomial time. Given a circuit C, we want to distinguish between the case that the circuit accepts most of its inputs and the case that the circuit always says no. It does not accept any string. This corresponds to the randomizing algorithms that have only one-sided error. All right. So we are given a circuit C. We want to distinguish between these two cases, accepts most strings or rejects all strings. What do we do? Well, we have the assumption that there is a hard function f. So, I mean, what can you do? You compute the hard function on the circuit. We compute it. But instead of just looking at the end result, we look at the gate values of the uniform circuit that computes the hard function. So remember, the hard function is computable by a uniform circuit of polynomial size and depth n squared. So here is the depth and here is the size. The depth is d n squared, the size is t, some big polynomial. We evaluate this circuit on the given input C, and we write down the gate values, exactly what each gate did in the computation. And we think of this as d rows, each row of length exactly t, representing the n squared steps in the computation. Is this clear? Good. So now, looking at this thing has a very nice structure. To compute an entry, say in the second row, it suffices to look at two entries in the row below it. Because we are looking at circuits that have fan-in 2, and this is how circuits work. Each gate is just a function of its fan-in the row below. We want to enforce additional useful structure on this set of rows to make our derandomization work. And to do so, we will use an approach that comes from the doubly efficient proof systems of Goldwasser, Kalai, and Rothblum. We think of this as a transformation of this matrix that comes from their doubly efficient proof system. And I'm going to really rush through this transformation. It's not crucial to get all the details here. So first, we encode each row by a low degree extension, essentially by the Reed-Muller code, without increasing its length too much. And in the first row, we have a low degree extension of the string C, padded with zeros. This is our inputs. So earlier we had these rows, and now we encoded them as polynomials. And now I just added space between the first two rows. So I did nothing, just did a visual thing of adding space. And between each pair of rows, we're going to add a bunch of additional polynomials. These will be constantly many polynomials that corresponds to an auxiliary small sum check protocol from the proof system of Goldwasser, Kalai, and Roth. And now let's just pack everything together again. This is the packed version where we encoded each row, and between each pair of rows, we added a bunch of polynomials that correspond to sum check. So the size t did not increase too much, and the depth also did not increase a lot because we only added constantly many rows between each pair. So the depth is now still to the order of n squared. And what we get from this GKR encoding of the circuit is a structure that we want. Let's go over it in detail. The first property, of course, each row is a code word in a nice code, the Reed-Muller code. By design, we encoded each row and then we added polynomials. So each row is a polynomial, it is a code word. The second property is that we have something similar to the one we started with, this downward self-reducibility. To compute each entry in a row, it suffices to look at a few entries in the row below it. And the third property is that the bottom row essentially corresponds to the input C, It is a low degree encoding of C. And in the bottom row, we have the low degree encoding of the output, f of C, because this is how a circuit works. In the top, we have the output. And we call such a thing a bootstrapping system for f of C. The bottom row contains C, the top row contains f of C. Each row is a code word in a nice code, and we have this downward self-reducibility property. Okay, given this encoding of the circuit, oh, one note, an alternative perspective of this encoding is that we can look at each row as the prover strategy function in the GKR doubly efficient proof system. I won't go into this in depth, it's just an alternative view of the same construction. The rows are just the prover strategy functions in a proof system. Okay, we have these encoding, these rows. Now we take each row, we think of it as the truth table of a hard function. I'm not claiming that it is a hard function. I'm saying that we think of it as the truth table of a function, and we apply the standard hardness versus randomness transformation that we know from our textbooks. Nissan-Wigderson, error correcting codes, designs, whatever you like. Apply it to the row, and we get a bunch of pseudo-random sets on the right side, each pseudo-random set corresponding to a row. We take their union, let's call it R sub C, and this is the pseudo-random set that we have for C. And this is how the non-Blackbox algorithm works. It takes the input C, computes the hard function, looks at the gate values in the circuit, encodes them using some specific, very useful encoding, then looks at each row, applies hardness versus randomness transformation, and takes the union of everything there. And what we want to claim is that this thing on the right is pseudo-random for C. Is this clear? I want to see if there are questions about the construction or about what we want to do now. Good. Let me mention the ideas in the proof. So the main lemma is a reconstruction lemma, which is a non-Blackbox version of classical reconstruction argument. It says that there is a probabilistic algorithm running in time n to the 100, such that for any fixed C, if that thing on the right, R sub C, is not a heating set for C, then this algorithm computes the hard function on C. So if R sub C does not full C, then we can compute F on C in time n to the 100. And it suffices for the proof, because we assume that F is hard on 100% of the inputs, which means that this algorithm can never succeed on any C, which means that for every C, that thing on the right is a heating set for C.
Hey, Roei, there's a question in the chat by Gopalakrishnan. He's asking if it's always possible to do this for any circuit to get this nice structure. Or I guess maybe the question is the same. He's asking, does the depth need to be n squared? Or?
Yeah, it's a good question. The depth does not need to be n squared to apply this transformation, get this nice structure. However, in the proof of the reconstruction lemma, we are going to use the fact that the depth is bounded. Any other questions? Okay. What I said had a tiny, there is something that I'm hiding under the rug. The circuit is not just uniform, it is log space uniform, meaning that there is a log space machine that can print it. I'm hiding this intentionally. I don't think it's crucial as a first order approximation to understand the result, but the transformation that I just mentioned, the encoding of the circuit, works for circuits that are log space uniform. So this is why I'm mentioning it right now, just to avoid confusion. But it does not depend on the depth. Okay, so let's just say in a couple of words what's going on in the reconstruction lemma. It's a non-Blackbox version of a classical argument from the late 90s. And we're going to quickly construct a compressed version of each row starting from the bottom and moving our way to the top. So assuming that there is a distinguisher, we are going to use this nice structure of the rows, such that for each row, we are going to compute a circuit of size, say, n to the 10, whose truth table is that row. And we will do this iteratively, first for the bottom row, then for the second row, and so on and so forth, until we reach the top row. And the top row has the output. When we reach the top row, we found f of c. And the crux, the crucial detail here, is that since the number of rows is bounded by n squared, by any fixed polynomial time, basically, the running time of this algorithm that works row by row is also bounded by some fixed polynomial, say n to the 100. So for example, if we spend time n to the 10 for each row and we work over n squared rows, we finished in time n to the 12, which is much shorter than n to the 100. And an alternative view of what's going on here is that we quickly reconstruct the prover strategy functions in a doubly efficient proof system that asserts the value f of c. Okay, I'm skipping over the technical details and just mentioning the crucial fact that this is instance-wise reconstruction. If the reconstruction, it should be succeeds. If the reconstruction succeeds at input C, then the derandomization succeeds at C. So wherever there is a distinguisher for each fixed C such that there is a distinguisher, the reconstruction succeeds on that specific C, which is impossible, it's a contradiction, and then the derandomization succeeds at this C. So you get that the hardness for this C implies derandomization for the same C. It's an instance-wise hardness versus randomness trade-off. And the result that we just saw is just the extreme case of this trade-off, where the function is hard on all inputs and therefore the derandomization succeeds on all inputs in the worst case. Okay, so we're about to conclude. Let's do a quick digest. So we saw a new way to do hardness versus randomness that crucially uses the input. It is totally uniform in terms of hypothesis and conclusion. It is non-black box, in the sense that we are going to produce randomness using the information in the input. And it is instance-wise, in the sense that the hardness versus randomness trade-off applies to each and every fixed input. We show something that might be the right hypothesis for worst-case derandomization, namely almost all inputs lower bounds. And we show that under appealing assumptions, randomness might be indistinguishable from useless. We can get rid of it effectively without paying anything. It's a free lunch randomization for decision problems and natural search problems. And this seems to be a promising area for further research. There are a lot of new directions to explore. For example, pushing this further towards an equivalence between derandomization and class separation on almost all inputs, finding sufficient and necessary hypotheses for free lunch derandomization, and applying these non-black box techniques and ideas and extending them in many other settings for derandomization, such as derandomization of log space or of proof systems and many other settings. And in case you like this and are interested and want to read further or see some more slides, so the paper is accessible. It's an ECCC, it has diagrams and explanations, and we use ticks, so there are pictures, so you can take a look at it. There are 2 slide decks available on Lige's website and on my website. So if you don't like my slides, Lige has completely different ones with other pictures and diagrams. And also we really like emails, so please feel more than welcome to drop us a line. That's it, everyone here and everyone listening. Thank you so much. Thank you.
Thanks, Roei. So yeah, we can take some questions before the recording, or I can also stop the recording and we can stay hanging out.
I think maybe we can stop the recording and see if people have questions.